Alright, WABYA here. This is going to be a very short video. I want to talk a little bit about common mode chokes for VLF and the medium frequencies, what I do here. This is also going to illustrate how I bring my lines, coaxial lines, in from the outside. It's just a small weatherproof box. We went ahead and bored a hole through the wall, and I've run some RG316 through it, soldered some pigtails onto some BNC connectors. Everything will be coming out the bottom of the box here, and we have an identical box on the outside. I guess what I should do is run outside, even though it's kind of raining. I'll open up that box and I'll show you the common mode chokes and talk a little bit about them. Alright, so what I did here is we're on the outside. I popped the cover off the box, the identical box as on the inside. What I'm going to do is take a little bit of hot glue gun, and we'll go ahead and seat the toroids so that they're all kind of spaced a little bit apart from each other. Try to minimize a little bit of interaction between them. What I've got is a total of 6 BNCs and 5 common mode chokes. And what I did is the very first BNC is a straight through connection. In other words, there's just some RG316 running from it over to the rightmost BNC on the inside. That way, if I ever want to run without any common mode choke, I can do some experimentation and just run it through that first BNC right there. These first 3 on the right are the type W core. That second one, you can see it's a little bit darker. That's actually a ferrite type 75 material, and then the one on the very left is a type W as well. So we'll go inside and I'll show you some of the tests that I did illustrating the common mode rejection that these chokes provide and their frequency response. I guess what I could do also is illustrate what we are doing on the outside. This is our little test bed for these loop antennas that I've been playing with. That outer loop is the WABYA modified U-loop, and what we've done is, coming off of the small amplifier box and the little bias T network that's in there, we've got a short length of some coax, some RG223 coming down into a weather tight box, and inside there is one of the common mode chokes, and then coming off of it on the output is it's a BNC connector as well, but I've got an adapter and it comes down and feeds some RG6 TV type cable. What I did is I put some 3:1 heat shrink tubing over all of the connections. These are really that heat shrink is really cool. It's adhesive lined, so as you heat it up and it's 3:1, it becomes quite gooey and performs provides a good mechanical connection, stiffens things up, but it also will keep water from getting into the connection. And then what I do is, where the heat shrink tubing hits the box on the bottom and on the top there, I run a bead of hot glue from hot glue gun. So the heat shrink tubing, no water can get in between the heat shrink tubing and the enclosures. So that's what we do all the way around. And the same thing on the U-loop, the modified U-loop. We've got a small jumper of RG316 coming up, and we've got the same type setup there. We've got some 3:1 heat shrink tubing around the BNC to type F adapter, and those are like 40 or 50 foot runs. Right now they're just coiled up on the ground here. So anyway, it's raining on me and it's about 45 degrees. I'm going to go ahead and get inside, and we'll show you some of the measure data from the lab downstairs on what these chokes are providing as far as common mode rejection. Empirically, I can tell you a huge improvement in the reduction of birdies and spurs and my overall noise floor using a common mode choke right at the feed point, and then inside the house, as you saw there, or actually on the outside of the house, box, but basically at the inside house interface. Alright, one thing I forgot to mention is now that the boxes have been installed onto the walls, I'm going to be shooting some of the expanding foam inside there, and that'll fill up the interface completely, sealing the outside. That way no bugs or cold air or water or anything can get in. I'm also, you can see I've got a straw. I'm going to put a couple of straws through there before I shoot the foam. That way, in case I want to run just some straight conductor, like a twisted pair or something for running some low voltage DC or something like that, I can just push it through the straw, and I'll have a small stuffing tube, if you will, through there. Alright, so let's get on and look at some of the test data. Alright, so you'll have to forgive me, this is a very, very crude way of illustrating these common mode chokes that I made up. I actually had a separate video where I talked about them before I mounted them in their enclosures along with test data and everything, and I lost that video. So you'll have to bear with me. We're going to pull up still images. These are like JPEGs and things like that. But here you can see I was experimenting with, this is the Type W core. There's approximately 20 turns of the RG316 coax on there, pigtail to a pair of BNC connectors. And over here we have the Type 75 core material. These two are currently mounted outside. One is going to the BYA modified U-loop antenna. The other one is going to the MLA 30 Plus. So just want to show you that's what they look like inside the enclosures. So again, my apologies for the way I'm having to present this, but alright. So this first plot here is a single Type W core, and let's see, yeah, that's a single Type W core. And what I've done is I'm sweeping up to 10 megahertz. Matter of fact, let me give myself a small pointer here. Yeah, you'll have to forgive me here. But you can see we're sweeping up to 10 meg. We're starting pretty close to just a couple of kilohertz. So the middle here, there's 10 divisions across here. The middle is 5 meg. And here's a reference signal along the top. And we've normalized that trace from the tracking generator. And I built up a special test jig where I came off the spectrum analyzer tracking generator combo to a pair of banana plugs to N connector, and we kept all the leads very, very short. We went ahead and normalized it, and then we kept the ground wire in place, and all we did was substitute in the core. So here you can see I've set up 4 markers, one there, one there, one there, and one there. There's really no reason to waste another one here at 10 meg because we can read it directly. And you can see here marker 1 I have set up at 100 kilohertz, 500 kilohertz, 2 meg, and then 5 meg. And these are the approximate common mode rejection in decibels, and it's fairly impressive at 100 kilohertz to have over 30 dB of common mode rejection. So that's why I'm noticing such an improvement in my noise floor and the reduction of birdies and hash and all kinds of RFI issues. And you can see at half a meg it jumps to 38 dB, and 2 meg 34, 5 meg at 30. So I'll try to speed this along, but that's what the Type W core looks like. So let's go ahead and look at the next picture here. Alright, so this one here is the Type 75 core. This is from Ferrite Corporation, and nothing has changed. We're still going up to 10 meg. everything is identical, but you'll notice the numbers are slightly different. Not quite as much rejection at the very lowest frequencies, and that's because the permeability of the core. The Type W core has slightly higher initial permeability, and that helps us get more reactance. Well, actually, the resistive component is higher down at the lower frequencies, and that makes it really useful for us. So let's now then, what I did is I overlaid one on top of the other so that it'd be easier to see what's going on. So this brown or orange trace is the Type W core, and this green trace is the Type 75 core. And you can see at the very, very lowest frequencies, because of that higher permeability, the Type W core actually would have more common mode rejection. And what's neat is as you move up in frequency, they pretty much become equal. Right there up to 10 meg, they're virtually identical. And just a slight difference down at the lower frequencies. So what I did then is I thought, alright, so now this is kind of a close-up of both of them. What I did is I changed the upper frequency to scan to only 2 megahertz. So this would be basically to the top end of 160 meters, basically the top of the broadcast band, and it lets us look a little bit closer at what's happening down here at the very, very low frequencies. In this case, the colors did swap. This here is the Type W core, and this is the Type 75, because I rescanned this plot, I regenerated it, because I had to renormalize everything because I changed my frequency span. So that's what this graph here is. A little bit close up of both of them going up to 2 meg. Alright, so here's the same plot, but what we're doing is we turned on the markers, and really there's no reason to show this. This is basically a repeat of some of the, it should be very close, within a few dB of the same data that we saw earlier. There's really no reason I should have shown that one, but alright, what do we got here? So what I did here is I had the bright idea. What would happen, let's see if I can back this up actually. Let's see if I can find it. Yeah, I sure can. Okay, so I thought it'd be interesting. Here's the Type 75 core, here's the Type W core, and what I did is I took a continuous length of the RG316 coax and I put one core directly after the other, and then I measured the common mode rejection. Now a lot of people would think, gosh, you know, if you've got 30 or so dB of this one and 35 dB of this one, that together, one after the other, you're going to end up with 65 dB. It doesn't work that way. You're just going to notice a slight increase when you add them together. So this is what I ended up measuring. And let me pull that graph back up. So let's see here. And there we go. Okay. So this is what we ended up getting. I ran this, we're just interested in the lower frequencies because we know that at the higher frequencies they pretty much equal out, but we do notice an improvement. There's even more common mode rejection when we add one after the other, and that's what the plot here is illustrating. It's not quite as smooth as it was before, but the absolute number is more impressive by, I don't know, probably about 4 or 5 dB. And let's see if we can, alright, what do we got? There we go. So this is an interesting plot because what I did here this bottom trace is the two chokes, one after the other, and this top trace is the type W by itself. And so you can see, since these are 5 decibels per division, yeah, we're getting about maybe about 7 dB at the most, and that's at about 1 meg. Down at the lower frequencies, we're seeing, yeah, maybe about 5 dB. In some places, we're only seeing a couple of dB. So, yeah, there is some improvement in common mode rejection, but it's probably not worth it, to be honest, given the cost of the cores and things like that. I think I'd be pretty happy with, for example, that top trace. That's going to provide one of those at the antenna and one of those right at the receiver or transceiver. Well, actually, we need to be careful. I would only use these in a receive situation. I haven't tested these to see how easily they saturate. For example, if you run 100 watts or maybe 500 watts through these cores, it'll be interesting to see how they tolerate heat and if their permeability changes. So for now, I would suggest using these for receive only, and these plots are applicable for a receive only case. But anyway, that's the type W compared to the case of the 2 cores together. And what do we got here? So this is a close-up now of the 2 cores together, and in this case I ran it up to just 1 meg. So this is kind of giving us a real close look at what we can expect. This is probably the ultimate common mode rejection that one could hope to achieve. This is a type W core followed by a type 75, a ferrite 75 core with magnetics type W. So that's the kind of numbers that we're getting, and that's up to 1 meg. Alright, let's go ahead and move this along. I don't want to put people to sleep here. Alright, and this is just a close-up. This is the same exact plot that you saw, but this time I've got markers showing the numbers. So you can see in the ultimate case, right at half a meg, we've got just shy of 43 decibels of rejection. But that's pretty impressive. You know, down at 50 kilohertz to get 26 decibels of common mode rejection is going to be very, very helpful. And at 100K we're over 33 and then hitting 40, so that's actually pretty good. So if you really, really wanted to have the ultimate rejection, you could put one after the other. Alright, so what do we got here? This is both cores, one after the other, but I know somebody might be interested in knowing what happens to the performance as we ran it up to the upper end of the HF spectrum up at 30 meg. So I thought I would just run this plot. It's very well mannered. There's no dips or peaks, any mysterious resonances or things like that. Very well mannered. You can see here at 30 meg we're getting just over 20 dB of common mode rejection, probably about 21, 22 dB. So it is useful all the way up to the top of 10 meter band. I'll just leave that on there in case you want to look at that for just a moment longer. And let's see what else we've got. Alright, so this here now, this is just an experiment that I tried. I took a very small type W core. This thing is tiny, and the reason I bought it is because it's much, much more economical. It's very inexpensive, but you can't get very many turns of even RG316 on here. So I thought I would try some This is Teflon coated silver wire, small gauge, twisted pair, and I thought I would make a common mode choke using twisted pair material, and I went ahead and tested it. And this is what it looked like. Let's make sure. Yeah. You know what? I think I lied. I got ahead of myself here. This is not what this is, because I'm noticing these numbers are in the 30s. So this is actually the same plot as before, but with the markers. My apologies for that. Sorry for the screw up. That's my big blunder. Gosh, totally blew it. Hate when I do that. Alright, this is the twisted pair small type W choke. And as you can see, it's very well mannered. I ran it up to 10 meg, but the common mode rejection is not nearly as good as using coaxial cable like RG316. So you'll notice these numbers here, yeah, pretty much almost 10 dB less than the RG316. So yeah, sorry about that mix up earlier. But this is the data for this choke here. I was just curious to see what twisted pair would do. And so it would work. You certainly are getting common mode rejection, and you're getting almost, 29 dB at half a meg, which is very, very respectable. 25 dB at 5 meg, 23 dB at 10 meg. Down in VLF, 100 kilohertz, getting a little over 18 dB. So certainly useful. So if you only had these very, very small cores, and these things, I'd have to measure them, but they're a little over an inch, OD, but they were very inexpensive, which is why I picked them up to experiment on them. So anyway, that's what I've got, and I just wanted to share my my chokes and how there we go. There's a difference showing. These chokes here are 1.4 inch OD, which is what I've been using, and you can see this one here is even smaller. It's like about an inch at the most, maybe even less than that. Might be like 0.87 or something. So, but they're a lot cheaper than these. Price of cores have gone up like crazy. It's really hard to get cores for the prices we were able to about even a year ago. So I'll go ahead and post this, and I hope this was of value and helps somebody out. 73 from WABYA.